Welcome students. In today's online lecture, we discuss the topic residue classes of integers modulo n, which is nothing but the base of that group of residue classes modulo n. So first we see the definition or statement of that division algorithm. So division algorithm states that let a be an integer and n a positive integer, then there are unique integers q and r such that a is equal to q into n plus r, where 0 is always less than or equal to r, which is less than n, that is r is here never negative. So here in this division we divide integer a by a positive integer n. So in the above equation, n is called divisor, a is called dividend, q is called quotient, and r is called remainder. So here r is always a positive and which is always less than n. Examples. So when we divide 17 by 5, then we get 17 is equal to 3 into 5 plus 2. So here 2 is the remainder when we divide 17 by 5. Again, when we divide 23 by 4, then we get 23 is equal to 5 into 4 plus 3. So here 3 is the remainder. Now another example. What happens when we divide minus 11 by 3? So when we divide minus 11 by 3, note that the remainder cannot be negative. So if you divide minus 11 by 3, then we get minus 11 is equal to minus 4 into 3 plus 1. So here the remainder, that is 1, is positive. Next point is nothing but modular arithmetic. Let a be an integer and n be a positive integer. We denote a mod n as the remainder when a is divided by n. So a mod n is nothing but a remainder when a is divided by the positive integer n. So examples, 9 mod 4. So when we divide 9 by 4, the remainder is nothing but 1. So 9 mod 4 is equal to 1 because 9 is equal to 2 into 4 plus 1. 12 mod 3. So 12 mod 3 is nothing but equal to 0 because 12 can be written as 4 into 3 plus 0. So 0 is the remainder. 7 mod 10. So 7 mod 10 is nothing but equal to 7 because 7 is equal to 0 into 10 plus 7. And minus 13 mod 4 is nothing but equal to 3 because we write minus 13 as minus 4 into 4 plus 3. So here this remainder is always positive. Now congruence is, let a and b be integers and n be a positive integer. Then we say that a is congruent to b modulo n if n divides a minus b. That is a minus b is nothing but equal to n into k. That is a minus b is multiple of n. Then we say that n divides a minus b. That is we can say a is congruent to b modulo n for some integer k. So we use the notation a is congruent to b modulo n to indicate that a is congruent to b modulo n integer n. In other words, a is congruent to b modulo n if and only if a mod n is equal to b mod n. We use the notation a is not congruent to b modulo n to indicate that a is incongruent to b modulo n. So we have that 12 congruent to 2 mod 5 because 12 minus 2, that is 10, is divisible by 5. 53 congruent to 5 modulo 8 because 53 minus 5 is 48, which is divisible by 8. 1000 congruent to 1 modulo 37 because 1000 minus 1, that is 999, is divisible by 37. But 23 is not congruent to 5 modulo 4 because 23 minus 5, that is 18, is not divisible by 4. Note that a is congruent to r modulo n if and only if n divides a minus r. So which is if and only if a minus r is multiple of n, that is a minus r is equal to n into k. So if and only if a is equal to k into n plus r. So a is congruent to r modulo n if and only if a can be written as k into n plus R. Thus, by division algorithm, A is congruent to R modulo n if and only if R is the remainder when we divide A by n. Now next one, that is residue classes modulo an integer n. So let R be a remainder when we divide given integer A by n, that is A is equal to n into k plus R. So by division algorithm we must have 0 is less than or equal to R is less than n. So here R is the remainder which is always greater than or equal to 0 and less than n. So that is possible values of R are nothing but in between that 0 and n, that is they are 0, 1, 2 up to n minus 1. So these are the possible values of R. Now we define residue classes of R and it is denoted by this notation, that is residue class of R, and is defined as residue class of R is nothing but equal to set of all x such that x is an integer such that x is congruent to R modulo n. That is residue class of R is nothing but equal to set of all x such that x is an integer such that x is equal to n into k plus R. That is residue class of R is nothing but equal to set of all x such that R is the remainder when we divide the integer x by n. So here when we divide the integer x by n, the remainder is R. So those x satisfying this condition R belongs to residue class of R. So since there are n minus 1 possible values of R, we get n minus 1 distinct residue classes such as class containing 0, class containing 1, class containing 2 up to class containing n minus 1 modulo n. And we denote the set of all residue classes modulo n by Zn. So Zn is nothing but set of all residue classes modulo n. So thus Zn is nothing but set containing all these residue classes. Illustration. So let n is equal to 5, then we divide any integer by n. So n is equal to 5 here. So possible values of remainders are 0 or 1 or 2 or 3 or 4. So we find all residue classes of these integers. So residue class of 0 is nothing but equal to set of all x such that x is an integer which leaves remainder 0 when divided by 5. So which are the integers which leaves remainder 0 when divided by 5? So all integers which are divisible by 5 are nothing but belongs to this residue class. So this is equal to set containing minus 10, minus 5, 0, 5, 10 and so on. So this is nothing but residue class of 0. Now next one, that is residue class of 1. That is when we divide the given integer by 5, then remainder must be equal to 1. So residue class of 1 contains those integer which leaves remainder 1 when we divide it by n. So residue class of 1 is nothing but set containing integers minus 9, minus 4, 1, 6, 11 and so on. So for example here, if we divide the integer 6 by 5, then remainder is 1. If we divide the integer 11 by 5, then also the remainder is 1. If we divide the integer minus 9 by 5, then also the remainder is 1. So this is nothing but residue class of 1. Also residue class of 2 is nothing but set of all integers that when we divide it by 5, the remainder is nothing but equal to 2. So the residue class of 2 is nothing but equal to set containing minus 8, minus 3, 2, 7, 12 and so on. Also residue class of 3 is nothing but equal to set containing integers minus 7, minus 2, 3, 8, 13 and so on. And lastly residue class of 4 is nothing but equal to set containing integers minus 6, minus 1, 4, 9, 14 and so on. Residue class of R is also denoted by this notation, that is R bar. Thus Z5 is nothing but set containing all these 5 residue classes, that is 0 bar, 1 bar, 2 bar, 3 bar and 4 bar. So is the set of residue classes modulo integer 5. So in general, Zn is nothing but the set of all residue classes modulo n, which contains elements 0 bar, 1 bar, 2 bar up to n minus 1 bar. So in general, Zn contains n elements. Note, n bar is equal to 0 bar, that is when we divide n by n, the remainder is 0. So n bar is equal to 0 bar. N plus 1 bar is nothing but equal to 1 bar, that is when we divide this number n plus 1 by n, the remainder is 1. So n plus 1 bar is 1 bar. Similarly, n plus 2 bar is nothing but equal to 2 bar, and so on. So this is about the residue class of integers modulo n. So thank you. In our next lecture, we see the group of residue classes modulo an integer n. So see you then. Goodbye.